Every great structure begins with a design, an intricate blend of calculations, materials, and imagination. For civil and structural engineers, the software we use, ETABS, Midas, Prota, Robot, StatPro, serves as our canvas. Beneath every beam, column, and slab lies an unseen foundation, the parameters we define for concrete. Are you using the right values? In this video, we will break down these critical design parameters, explain why they matter, and show you how to get them right, no matter which software you are using. Let's dive in. In this short presentation, we are going to talk about the following design parameters. We will talk about normal concrete unit weight. We'll talk about the modulus of elasticity. We'll talk about Poisson's ratio, shear modulus, bulk modulus, and we'll also talk about the coefficient of thermal expansion. Unit weight of concrete. According to Eurocode 1, clause 3.2.1, for unreinforced concrete, the unit weight is 24 kilonewtons per meter cubed, and for reinforced concrete, the unit weight is 25 kilonewtons per meter cubed. The unit weight of the reinforced concrete is way much higher than that of unreinforced concrete. The reason behind this is because reinforced concrete has got rebars, and these rebars are way much denser than the concrete itself, making the unit weight slightly higher than that of unreinforced concrete. We go ahead and talk about the modulus of elasticity for different concrete strengths. In this table, we see that the modulus of elasticity increases the higher the concrete grade. For example, for C20 grade of concrete, we have a modulus of elasticity of 31.1 gigapascals. As we move down to C35, the concrete modulus of elasticity also goes up. For C35, we have a modulus of elasticity of 35.8 gigapascals. Let's look at how we would find the modulus of elasticity given a concrete grade. We see that EC is the notation for a modulus of elasticity. FCM is the mean compressive strength of concrete. For us to find FCM, we have to add the characteristic compressive strength. We have to add 8 megapascals, and that is what is going to give us the mean compressive strength. Here is a calculation example. Let's say we have a concrete grade of 20 megapascals. The first thing we do is we determine FCM, which is the mean compressive strength. In this case, we add 20 plus 8 to get 28 megapascals. Once we get the 28 megapascals, we just simply replace it in the formula, and we get a modulus of elasticity of 31.1 gigapascal for a concrete grade of 20 megapascals. Next, we are going to look at Poisson's ratio. The Poisson's ratio describes the relationship between the axial strains and the lateral strains. According to Eurocode 2, for uncracked concrete, the Poisson's ratio is typically taken as 0.2. In most concrete designs, this value of concrete Poisson's ratio ranges from 0.18 to 0.2. For uncracked concrete, it would mean that the Poisson's ratio would fall all the way to 0. Now, let us look at the effects of high and low Poisson's ratio. What are the effects on lateral deformation, on volumetric changes, on cracking risk, on flexibility, tensile performance, and what are some of the applications of a low and high Poisson's ratio? In relation to lateral deformation, a higher Poisson's ratio leads to increased bulging under compressive loads. A higher Poisson's ratio will reduce the volume changes in concrete. Concrete remains closer to incompressible. A higher Poisson's ratio is going to increase the risk of cracking. Lateral expansion induces tensile stresses. A higher Poisson's ratio will make the concrete more flexible, and the concrete will be able to handle minor deformations. A higher Poisson's ratio will make the tensile performance of concrete poor. The concrete will be prone to cracking under tension. In what instances is a higher Poisson's ratio preferred? It is preferred in prestressed concrete and in structures that require ductility. Let us talk about low Poisson's ratio. What are some of the effects on lateral deformation? We are going to see that if we have a low Poisson's ratio, there is going to be minimal bulging under compressive loads. There is going to be an increased volumetric change as the concrete is going to be prone to shrinkage and curling. A low Poisson's ratio will increase the risk of cracking. It makes the concrete at risk of brittle failure under tension. A low Poisson's ratio is going to make the concrete less flexible. It's going to make it prone to fracture. A low Poisson's ratio is going to make the tensile performance of concrete poor. Cracks propagate due to brittleness. The application of a low Poisson's ratio concrete can be in foundations, in columns, and rigid structures. Shear modulus. The shear modulus G of concrete, also known as the modulus of rigidity, can be calculated by using the Poisson's ratio and the modulus of elasticity. This is according to Eurocode 2. Here we see the formula to use when we are finding the shear modulus. So if we have E, the modulus of elasticity, and if we have V, then we can find the shear modulus. So for a Poisson's ratio of 0.2, the shear modulus is approximately 0.42 of the elastic modulus. In this pop-up, we see that if we have a force that is acting on this area, this force is going to cause a shear stress. The height from here to the top is L, and when this force acts here, it is going to cause a displacement. A force that is acting parallel on an area, as shown here, is going to give us the shear stress. And then the displacement divided by the length is going to give us the shear strain. Dividing This tool is going to give us the shear modulus. What are some of the applications of the shear modulus? The shear modulus is essential for analyzing torsion in structural elements. It's also important when we are analyzing shear deformation in slabs, beams, and other structural members. The shear modulus is important in finite element modeling that involves 3D stress-strain relationships. Next, we talk about the bulk modulus. The bulk modulus K of concrete represents its resistance to uniform compression. The bulk modulus is related to the elastic modulus and the Poisson's ratio. This is according to the principles that are outlined in the Eurocodes. If we have a Poisson's ratio of 0.2, the bulk modulus is approximately 0.56 of the elastic modulus. What are some of the applications of the bulk modulus? The bulk modulus is used to assess the volume change analysis under hydrostatic stress. Example in pressure vessels, dams, and deep foundations. It is used in understanding deformation under uniform compression. The bulk modulus is also used as inputs for finite element modeling in multi-axial stress conditions. Coefficient of thermal expansion. In large concrete structures such as bridges, temperature fluctuations can induce thermal stresses that must be carefully be considered in the design process. The coefficient of thermal expansion plays a critical role in determining how much the concrete will expand and contract in relation to the changes in temperature. Clause 3.1.3 states that the coefficient of thermal expansion, alpha T, for concrete can typically be taken as alpha T is equal to 10 times 10 to the power negative 6. This value ranges from 10 times 10 to the power negative 6 to 12 times 10 to the power negative 6 per degree Celsius. Practical use. The coefficient of thermal expansion is used to calculate the thermal stresses and strains in concrete structures which are subjected to temperature variations. So these buildings can be bridges, they can be large buildings, they can be dams, they can be industrial facilities with high thermal exposure.